Now, halohydrins are simply molecules that kind of look like this. It'd be an X here, and whatever else is here. That's what a halohydrin is. To form those, very simple. Take an alkene plus your halogen in the presence of water, and you will get a halohydrin. Just like that. So let's take a look at the mechanism of that. And let's do chlorohydrin. All right, no problem. Same as always, do the mechanism. Knowing where the electrons go is the whole battle, really. Pi bond attacks the chlorine, chloride leaves, and these lone pairs come down onto that carbon. That's the first step. That's the formation of the chloronium ion. Now remember, the chlorine can come in from the top or the bottom of this particular alkene. Positive charge is there. So now instead of the chloride coming back, water will come in, because water is more plentiful, first of all. Second of all, the chloride is going to be wrapped up in dipole ion interaction with the water. So again, the chloronium ion is down, so the water must come in from the side opposite that. So the bond there will break. So this is an anti-addition. There you go. And of course, you have a protonated alcohol, so that'll deprotonate to give you the halohydrin. Oops, not X, chlorine. And there you go. So that's the mechanism. Now, take a look in your notes. Now compare this mechanism to the mechanism of the addition of chlorine across the double bond, where there was no water. And you're going to see the mechanisms are remarkably similar. Different players of the same game. So keep that in mind. We're learning a lot of mechanism in this chapter, but we're also seeing a lot of the same things. A lot of the same themes are recurring. So get your mind to start seeing the themes that are occurring, and then these mechanisms will be fairly easy to do. So let's do another example of forming a halohydrin, and let's take a closer look at the nucleophile and where it's attacking. Okay, so again, first step. There we go. Pi bond attacks the bromine. Bond breaks, and these electrons go into there. So you form the bromonium ion in this case. And I always like to put my ions down. Could have drawn it up. I just choose to put them down because I think it looks prettier, neater, cleaner, however you want to say it. Plus charge is there. So now, I have water I need to add to this. Now the water can attack here, or it can attack here. Now, it's an SN2-like reaction, because remember we have the nucleophile is going to attack here, pi bond, and this leaving group is going to leave. The ring is going to open, Essentially, the ring opening is the leaving group leaving. But why is it attacking the most substituted carbon? And the reason is this. This carbon is extremely delta positive. It's more delta positive than just a normal little polarization. It's very, very delta positive. It's so delta positive that this is not really a true tetrahedral. It's going to have a lot more trigonal planar characteristics, and that's going to allow the water, the room, to come in here and attack that carbon. In a normal situation where this bromine wasn't positive and wasn't also in a 3-membered ring, you wouldn't be able to do that. But because it's a bromonium ion and it's trapped, and bromonium ions are a 3-membered ring, the water can now attack, or the nucleophile, doesn't have to be water, can now attack the more substituted carbon in an SN2-like fashion. So keep that in mind. Even though it's an SN2-like reaction, it will attack the more substituted carbon because that's where the greater delta positive is. And the greater delta positive causes the carbocation to, if you will, flatten out a little bit, to be less tetrahedral than normal, simply because it has a large delta positive. It's not a true cation. It's not a cation. It's just a large, large, large delta positive. The bigger your delta positive, the more cation tendency you have, the more trigonal planar tendency or structure you'll have. And then, of course, more water will deprotonate our alcohol, or protonated alcohol, and that gives us our chlorohydrin. Plus the enantiomer. There you go. So that's why we're attacking the more substituted carbon.